Welcome to Maths with EJD. We have been talking about basic calculus and especially integration in the last few videos. This is the fourth one in the integration series. And now the focus turns to integration of derivative function ratios. So this whole thing just simply talks about whenever you have to integrate a function that is like f prime of x divided by f of x dx. How do you treat this? First of all, how do you identify it? And then when you identify it, how do you differentiate that? That is what that is simply about. So you have a derivative at the top and you have the function whose derivative you have at the top, you have it at the bottom. You have a derivative numerator and the function denominator. So how do you integrate that? That's what this is about. First, let's look at something really close to that. You have you remember already, we know how to integrate polynomial functions, right? So if you try to evaluate integral of 1 over x dx using the previous method, right? Using that method of, express it like a polynomial, increase the power by 1 and divide by the new power. Let's see how that happens here. So, all you have here will be integral of 1 over x dx. And 1 over x, is x raised power minus 1. So it's more like you have integral of x raised power minus 1 dx. So if you follow that polynomial style, so it means you're going to have x raised power minus 1 plus 1 divided by minus 1 plus 1, then plus an arbitrary constant c. But then, minus 1 plus 1 is 0. So you have x raised power 0, which is okay. But then minus 1 plus 1 down here is 0. So that's looking like a bad idea because dividing by 0, like you saw under limits, is a problem, So x raised power 0 divided by 0 plus c. And then x raised power 0 is 1 divided by 0 plus c. So 1 divided by 0 is undefined. So the whole thing breaks down. So we can't proceed using that method for polynomials for this kind of thing. So you see, this method is not helpful because the result is undefined. So it means we have to look for better ways. And that's what takes us to what we are considering for today. So if you think of integration as anti-differentiation, that was the first idea I told you about under basic principles of integration. So if you think of integration as anti-differentiation, we see that d dx of ln x is 1 over x. You remember when we're talking about logarithmic functions, right? If you have a logarithmic function ln x, so if you differentiate this, if this is y, so if you do dy dx for ln x, that means differentiate x, you get 1, and divide by the original value, if you remember very well. So you can see the knowledge of differentiation is very useful even in integration. So if you do not understand differentiation properly, you're going to have issues with integration. So you remember that when you differentiate ln x, you get 1 over x. Ln x is the natural logarithm of x, okay? So you get 1 over x. So if you now see it that way, then you can say, if you follow that principle, you can now say d dx of ln f of x, as you can see, is f prime of x over f of x. Following this idea now, so ln f of x, ln x, if you differentiate ln x, that means differentiate x, you get 1, and put the original thing. So this 1 now is like f prime of x, and the x itself is the original f of x. Now you see that d dx of ln f of x now is the same thing as f prime of x over f of x. So we can use this idea. So we can now say, since d dx of ln x is 1 over x, then we can have 1 over x dx equals d ln x. As you can see, you have 1 over x, d dx of ln x is 1 over x. So it's like we are just transferring this down here. So dx goes to the other side. So you have 1 over x dx equals d ln x. That's what you have right here. Okay. And since that is taken care of, we can navigate from here. All right. So this comes down to become this. So 1 over x dx equals d ln x. Now, so if you integrate both sides, you have integral of 1 over x dx, integral of d ln x. Now, one thing in integration you should be aware of is integral of d anything is that thing. So if your name is Tayo, for instance, integral of d Tayo is equal to Tayo. Okay? Integral of course, plus arbitrary constant c. Integral of dy is equal to y plus c. So in the same way, integral of d ln x will simply be ln x plus c. So that integral you couldn't do before, now we are able to do it. So we can now say integral of 1 over x dx is equal to ln x plus c. which is the arbitrary constant. So we can use the idea of anti-differentiation to take care of issues like that. And generally speaking, so that simply means that, okay, of course, I think I'm jumping the gun. Let's go to, okay, the next slide to establish what I intended to establish. Now, right here, we have the law settled. So you discovered now that whenever you have to evaluate this integral of f prime of x divided by f of x dx, the simple answer would just be the ln of the denominator. So whenever you have this kind of thing, the integral is the ln of what you have at the bottom. So integral of f prime of x over f of x dx is simply the ln of f of x plus c. Easy. So, and it is obvious that integral of 1 over x dx is simply the ln of x, as we have seen already. So ln of x plus c. So on a general note, we have this law for differentiation of derivative function ratio. So derivative function ratio puts over themselves, that's why it's ratio. So integral of f prime of x over f of x dx is the same thing as ln of f of x plus c. So that's the rule established. So with this now, you can easily brave this kind of questions. So let's see some examples. You have example 1 here. Evaluate 4x plus 3 divided by 2x squared plus 3x minus 1 dx. Now, it may be looking all difficult, but one of the first things you want to check, of course, whenever you have something like this, the first thing you want to see is, can you divide through? So that, you remember there was a case where we had something at the top and we have only x at the bottom. So in that case, we could divide through by x and we go on. But here, you can see that it's not possible to so divide. So the next thing you want to check is, okay, if you differentiate this bottom, are you going to get the top? So if that happens, then you just know the integral is simply going to be the ln of the bottom, basically. So if you differentiate the denominator and you get the numerator, so the integral of that function will simply be equal to the ln of the denominator, simply. Okay, so the first thing you want to check is if the derivative of this is equal to this. So it is clear that d dx of 2x squared plus 3x minus 1 is the same thing as 4x plus 3. Differentiate 2x squared, you get 4x. Differentiate 3x, you get 3. So it's exactly what you have at the top. So if that is the case, you don't have to stress it too much. Just say, then the integral of 4x plus 3 divided by 2x squared plus 3x minus 1 dx is simply the ln of the base, the denominator, plus the constant c. Another way in which you can do this, we are going to see that under substitution, algebraic substitution. So you can just say, let u be this, and then you do all that, and then at the end of the day, it ends up canceling out 4x plus 3, and then you get your result. So this is ln 2x squared plus 3x minus 1 plus c. So differentiate this. If you get this, the answer is the ln of what you differentiated, basically. So it's so simple and straight to the point. Okay, so let's take another example, maybe something a bit not as straightforward. So here, you want to evaluate integral of x plus 1 divided by x squared plus 2x plus 1 dx. So, of course, you can see that it cannot divide like what the first kind of encounter we had with this kind of thing. The next thing is check d dx of x squared plus 2x plus 1. That is 2 into x plus 2. And that's the same thing as 2 into x plus 1. Now, the trouble here is that what we have here is x plus 1. But the derivative of what you have at the base is 2x plus 1. So we have to find a way. Having 2x plus 1 already is a good sign. But then you have to find a way of taking care of that too. So if you want to do that, you just come and say integral of x plus 1 divided by x squared plus 2x plus 1 dx is the same thing, of course, as integral of 1 times x plus 1. So anytime I introduce one, you should already know that we are trying to do some skillful maneuver, all right? And so since 1 times x plus 1 is the same thing, and you now know that 1 can be anything. 1 can be half times 2. We have 2 here. So it helps us to know that 1 is half times 2. So I just come instead for this one, I have half times 2. Nothing has changed. So the next thing is I can bring the half out here. So we have half outside, and it looks like we have got our deal, So you have half integral of 2x plus 1 into x squared plus 2x plus 1 dx. Now, if you differentiate x squared plus 2x plus 1, you get the expansion of 2 into x plus 1, which is 2x plus 2. So with that now, you have half outside, and then you have ln of x squared plus 2x plus 1 plus c. So in some cases, you're going to have this kind of situation. So you have 2 into x plus 1, which is not exactly like what you have here, but then you can find your way of making it happen, by introducing something like this, and then you end up getting this result. And with that, we've come to the end of derivative function ratio, how to integrate that. So make sure you subscribe and press the notification bell so you can always get other videos that will come. So thanks for listening.